Yeah. All right, well, I just went over what I did in class last time, which was maybe mostly in a video. And I, combined gas law, Avogadro's, ideal gas density. Sorry to go through this so fast, but I already said all this. So we're going to be doing stoichiometry problems with gases. And the first one we'll work on is activity 5, number 18. I posted the solutions to everything through activity 4, except for the problems that have been assigned as graded assignment problems. So I'm posting them as I go along. So if we look at this problem, it's nitrogen and hydrogen gases are contained in a balloon. Okay, so let me just go over the first line, whose pressure is always equal to atmospheric pressure. The pressure is therefore constant. I mean, all this stuff is a little bit like Greek, right? But let me sort of explain what that means. So we have this balloon, and we've got nitrogen, and we've got hydrogen in it. Oh, H3, H2. I'm looking at the 3 here, and you know what balloons are made of? They're rather flimsy, not very strong material, which is why you're allowed to say that the pressure inside would be the same as the pressure outside. So it would be really impossible to pressurize inside a balloon because the rubber isn't going to hold it. So it's really going to end up equalizing with the pressure outside. So P inside is going to be the same as P outside. And the outside pressure, of course, is atmospheric pressure. All right, so whenever there's a problem in a balloon, basically the pressure inside can always be assumed to equal the pressure outside. And that's why the pressure inside will be constant, because it'll be whatever the outside pressure is. Okay, so that's number 1. Okay, number 2, let's look at what this problem is about. Okay, so it says initially there is 1 mole of nitrogen and 3 moles of hydrogen present. Okay, that's about the easiest mole ratio I could possibly give, because it reflects the mole ratio, the stoichiometric ratio, which is 1 to 3. Okay, and then you form 2 here. So we've got some interesting stoichiometry in this problem, which is really why I picked it. So, okay, so it says, what is the initial volume at standard temperature and pressure? Okay, so standard temperature and pressure, if it's telling you that that's, this thing is at STP, that means that we're going to have a pressure of 1 atmosphere outside, which is the same as inside, right? So that's going to be 1 atmosphere. We also know that the temperature is going to be 273 Kelvin, because that's what STP is. That is the standard temperature, and this is the standard pressure. Okay, so these guys are constant. So if we look at this reaction now, we have 1 N2 plus 3 H2 goes to 2 NH3, and these are all, of course, gases. So if you start with 1 mole of N2 and 3 moles of H2, we have 4 moles that are present at the beginning, all right? But at the end, now we only form, for every 1 mole of N2 and 3 moles of H2 that react, and we only have 1 mole of N2 and 3 of H2, we're going to end up with 2 moles that are present at the end. So what has happened is, the temperature and pressure have stayed the same. They are exactly the same as they were before. So what's changing is the number of moles. And it goes from 4 to 2. So if we're going to figure out the volume, well, we know from Avogadro's law that the volume is proportional to the moles. And the only thing that changes here, so the only thing changing is N. So V is going to be proportional to N. And so if N drops, that means that the volume is going to drop. Not only do we know it's going to drop, we know it's going to drop by a factor of 2. Okay, so what we're going to do in this problem is we're going to figure out the initial volume, and then we're going to see that the final volume is just half of the initial volume. So let me show you that, you could easily calculate the initial volume, V, from nRT over P, right, using the ideal gas law. And then you could put in the number of moles as 4. So 4 moles. 0.08206 liter atmospheres, mole Kelvin, 273. And then the pressure, sorry, which is 1 atmosphere, the same outside as inside because it's in a balloon. All right, so if you do this math here, it comes out to 89.6 liters. Okay, that's the initial volume. So the final volume, well, now at the end, I only have 2 moles. So N is equal to 2. So instead of 4 times all this stuff, I now have 2 times the same stuff. Right, so it's going to come out to half of what we just calculated, which is 44.8 liters. But you didn't even have to do that because that V is proportional to N. So you could use V1 over N1 is equal to V2 over N2. Or you could just do it in your head. The moles goes down by a factor of 2. The volume's going to go down by a factor of 2, but you could always use this formula. So you would end up with V1 times the ratio of N2 over N1, which is 2 over 4, or 1/2, equals V2. And so you could get the answer that way as well. But I want to go back to this calculation because I kind of assumed something. I kind of pulled a fast one a little bit, And what I did that wasn't really yet justified was, look at this. I took this number of moles. I took the total moles here. And I assumed that the total moles would work. But we've never really talked about what we do when we have gas mixtures. So this was for, initially anyway, you had hydrogen and nitrogen. You had 3 moles of one, right? You had this 4 is 1 plus 3, right? It's the total number of moles. So I that really is an assumption. So what I assume is that when there's a gas mixture, okay, you can just take the total moles and use it in the ideal gas law. Okay, but that's not something that's necessarily obvious. Well, it turns out that it's actually true. Okay, so I didn't lie or anything. This actually is true. Okay, and actually, what we say is that there's an ideal gas law for total moles relating to total pressure and there's also an ideal gas law for moles of each component, which means each of the gases in a mixture relating to what we call a partial pressure. So in our case, we were actually solving for the volume, but this pressure here is actually the total pressure inside. Well, actually here's where I had the mixture. This is actually the total pressure inside that balloon. And what it really consists of is a pressure due to one of the gases and a pressure due to the other gases. So when you have a gas mixture, so suppose we have a mixture of gas A and gas B, okay? That means that we can say that P total is the total moles RT over V, which you can see that that's the ideal gas law for total moles. All right, so I just put total here and here on the P and the N. But we also have a partial pressure. So this is called the partial pressure of gas A. And we also have a partial pressure of gas B, okay? So look at this. We have an ideal gas law, P equals nRT over V for each of the component gases. And we have an ideal gas law for the total. And, okay. So, well, what does it mean, a partial pressure? So what is a partial pressure? Well, if only gas A was there, so suppose we had only gas A, by the ideal gas law, the pressure would be the moles of A times RT over V. It would be PA. So that implies that what the partial pressure is, this is the pressure of a gas. So the partial pressure of a gas in a mixture is the pressure that gas would exert if it was the only gas there. So you can kind of draw almost a silly, cartoonish kind of picture on this, right? You have a volume. Okay, and suppose I have a bunch of gas B. I'm going to draw 15 dots, big blobs of gas molecules, which is really pretty inaccurate. But anyway, I have 15 molecules of B, let's say, and only 5 of A. Okay, and if I take out, so I have the same container, but now let's suppose I've taken out all of the B molecules. So I only have the A molecules, right? So this would be the partial pressure of A, which would be NA-RT over V. And really, NA is the only moles, so that would be N total here. So it would just be nRT over V, which the ideal gas law tells us that would be the total pressure if only A were present. And if you had B, I could do the same thing. Okay, PB and B RT over V. And here we have P total. So the total pressure, turns out, is actually the sum of those partial pressures. And if you have more than 2 gases, you would have to add up all of their partial pressures. So what it's really saying is that gas A is exerting a certain pressure, and it's really dependent on the amount of A. Gas B is determining a pressure determined by the amount of B. And the pressure that A exerts has nothing to do with what else is present. It would be exerting that pressure if it were by itself or with 1 gas or with 25 gases. Okay, so so this guy here, this is called Dalton's law of partial pressures. You don't need to know that name. And you could see here that I have the pressures of the different components. And we also know that the total pressure is N total RT over V. So when I did that calculation with the 4 moles, which was the total, and I used the ideal gas law, may have looked like I was pulling a fast one, but actually it's correct. I just didn't go over that at that point. So these are partial pressures. And they, like I said, they depend directly on the number of moles of that gas present. In fact, you can kind of have a relation like this. You could say that the partial pressure of A is to the total pressure as the moles of A is to the total moles. So the portion of the total pressure that's due to A, well, that's just really the portion of moles of the total that's due to A. And so, this leads to the mathematical relation PA over P total is NA over N total. But I would really like to be able to prove this, right? Not just tell that to you. And it's totally pretty easily provable using the expressions I just taught you. So PA is NA RT over V, and P total is N total RT over V. So if I take PA and divide it by P total, that's NA over N total. NA, oh, let me show you. Let me do it out. NA RT over V divided by N total RT over V. And here, everything cancels out except for NA over N total. So yes, PA over P total does equal NA over N total. Okay, now, what is this NA over N total? Does anybody know what that's called? Anybody seen that before or heard of it? Or even if you didn't know what it was called, yeah, what? James, I thought you were raising your hand, you're stretching. You can't stretch in your own house without being asked to answer a question. But you can see that this is a fraction of moles that's due to A, right? It's the number of moles of A divided by the total. And we call that the mole fraction of A, okay? So that means that the ratio here, PA over P total, is equal to XA. And that also means that if I take my mole fraction and multiply by the total pressure, I get the partial pressure. And I'm not telling you this to torture you or anything. This actually makes some problems easier. And I'm going to show you one right now. Okay, so does anybody want me to go back over anything before I move?
I do. You lost me at like P total, N total, like the cross multiplying. I don't know what you're talking about.
Hold on. You mean like over here?
Yeah, well, like I understood the boxes. Like, okay, I get it. Like, there's two different for PA, and I got that. But then beneath it, it's just too complete. You go way too fast.
All right, let me go over it again, okay?
Okay, thank you.
Yeah, no problem. Okay, so I guess what I'm trying to get across is that the partial pressure simply depends on the amount of the gas you have there. And if you have a greater number of moles of A, then you're going to have a greater partial pressure of A. You could see that right here because, PA is NA RT over V, right? If it was different, then it really depends on this number of moles. So if you have a mixture and you have a large fraction of A, let's say, so you have more A, here, let's use what we have here. We have more B than A, okay? So that means that you would expect that, you would have a smaller partial pressure of A because you have smaller number of moles in the total of A, so that the partial pressure of A is related to the total pressure the way the moles of A is related to the total moles, that it's the same ratio. So PA over P total is NA over N total. Does that make a little more sense?
Yeah, okay, I got it. Yeah, because they're not as much as PB.
That's right. And in fact, PB over P total would equal NB over N total, would be the mole fraction of B. Okay. Well, anyway, so this here, oh, something got erased. Wait a minute. Uh-oh. right? So what this is just showing is how mathematically you could show that, which, you know, if you're not interested, you can just ignore it, really, as long as you understand that these two things are equal. So since we have this formula, PA over P total is NA over N total, and NA over N total, well, that's just a fraction of moles, that's A. So that means that the pressure ratio of A to total pressure is just the mole fraction of A. So the fraction of the pressure that's due to A is equal to the mole fraction of A. Okay? Does that make it a little better?
Yes, thank you.
All right, okay. So let me go and do this problem now. Right, so we have a mixture of N2 and AR, argon and nitrogen gases, and it's telling you how many moles you have of nitrogen and how many moles you have of argon. So you can see here that you have a much greater amount of moles of nitrogen than argon. And then you're also given the temperature and the volume. And you're asked to calculate what is the partial pressure of each component and what is the total pressure. So you actually have a lot of choice on how to do this problem. So one way you could do it is you could find the total pressure, okay? And you could use the total moles to do that. So P total would be N total RT over V, okay? And then we could also calculate PN2. What would I put here? What's different in this formula for the partial pressure of N2? What would I write here first?
Moles of nitrogen.
Mm-hmm. That's right. And then PAR would be NAR RT over V. Okay, so let's just calculate the P total. So if you add up the moles, 15 plus 5, that's 20. That's N total. So it's just 20. R 0.08206. T is 298. And the volume is 500 liters. It's a lot of volume there. So this comes out to it's almost one atmosphere, 0.978 atmospheres. So, and I could calculate PN2 and PAR the same way. It would just be with 15 R T over V. Notice all the gases have 500 liters as their volume. N2 and argon are both in the same container, so they have the same volume. It's just the container volume. And argon, precisely the same calculation. So there's a lot of writing involved with doing the calculation this way. And this would come out to 0.245 and 0.734. So that's one way you can do the problem. You could basically do the same problem 3 times with 3 different numbers of moles. But let's say you didn't want to do that and you want to make it a little easier on yourself. You'd say, okay, well, PN2, that's the mole fraction of N2 times the total pressure. So you could take a look at these moles and you could say, oh, NN2, that's a pretty easy calculation. This is the moles of N2 and the total moles. So you could see that that is 0.750. That's the mole fraction of nitrogen, which also tells you what is the mole fraction of argon going to be. If the mole fraction of N2 is 0.750, what's the mole fraction? What do fractions all have to add up to? Come on, what do fractions add up to?
One.
So that would be 0.250 to 3 sig figs, because really 1 is infinitely significant. So this would be the mole fraction of argon. So Pn2 would be 0.750 times the total pressure, which we calculated right here, or 0.978. This has a unit. The fraction does not have a unit, because fractions are unitless, which comes out to 0.734. So I could also do the same thing to get the P argon, right? I could take 0.25 times the total pressure, X argon times total pressure, and I would get 0.245. But after I did this calculation, I could actually calculate P argon a different way. I could use the fact that the sum of the partial pressures equals the total pressure, right? So that means that P total minus Pn2 is P argon. So I could have done 0.978 minus 0.734 and gotten 0.245. I could have solved for it this way. So there's different ways you can do this. You only really have to make sure you can do it one correct way. You have to do them all the ways. So does that make sense?
Excuse me.
Yeah.
So I got a little bit lost and I didn't get where the 1 came from.
Oh, because the mole fraction of argon plus the mole fraction of nitrogen has to equal 1, because fractions always add up to 1. You know, all the pieces of the pie have to add up to the whole pie.
Oh, all right. I
Only
get it.
argon and nitrogen, they have to, mole fractions must add up to 1.
Right, thank you.
Good, I'm glad. All right, so this is just a partial pressure, sorry?
Yeah, I have a question. So what's the answer?
What's the answer? Oh,
Question.
what was the question? Was what is the partial pressure of each?
Because there's so much math here, that's kind of confusing.
You're coming in so light, I can hardly hear you.
Oh, so I'm asking, like, what's the answer to the question?
Right, well, the question was, what is the partial pressure of each component and what is the total pressure? So we've gotten that. That's one answer. These are other answers. And then I was really just showing you different way to do it.
Oh, so then from there it cuts off. Okay.
So, I mean, I could have stopped right here and said, that's the answer.
Okay.
But what I wanted to show you is that you don't have to do this calculation 3 times. You can actually do it based on, you know, your total pressure and the mole fraction, right, of each component. You can get the partial pressures that way.
Okay.
Anyway, that's all. Okay, good. Any other questions? All right. Okay, so what I'm going to do next is go over this problem. I'm going to do this problem. So let's see. This is these are gas stoichiometry problems. You remember stoichiometry problems, right, from last semester? So stoichiometry problems, right? That's where you're given the amount of a reactant or product. You need to find the amount of reactant or product from that, a different reactant or product. But now, you know, we're talking about examples where a gas is produced or maybe a gas reacts. And so it's basically the same kind of thing where you have to go, you have to get moles. You know, we used to call them, you know, if you started with grams of a reactant, you want to end up with grams of a product, you have to go grams to moles to moles to grams. You can't go directly from grams to grams. Well, in problems like this, it's really the same thing. You've got to get to moles of of either reactant or product, and then get moles of a different reactant or product. But now, instead of being given information about, well, now gases can be involved as well. So for example, you could be asked, well, what is the pressure at the end of that reaction? So then you have to go from moles to pressure. All right, so it's a little bit of a twist. Every time we do a different thing, we add another level of complexity. So, okay, so here's an example. This is from activity 6. So you should have it. So look at this reaction. We've got a certain volume of acid solution, HCl. So let's write it down because we're going to write the reaction down. Plus calcium carbonate, which is a solid. React with excess calcium carbonate. And this, I don't know how well you studied these last semester, but when I teach 103, I call this acid plus carbonate. Does anybody know what gas is formed in this reaction? If you had done lab in person, I'm sure you would remember this because it's a giant block of calcium carbonates put in with acid, and there's bubbles that come out. And anybody know what those bubbles are? Just take a guess. Look at the
Carbon dioxide.
Carbon dioxide, yeah. And also water. And also calcium chloride. Okay. And there's H2O. This is actually a 2-to-1 ratio here. And everything else is a 1. So this is pretty straightforward stoichiometry. So this is a gas forming reaction. All right, so now it says, so you're given the amount of HCl that reacts in the form of a solution, and you're given the molarity and the volume. So you could use the molarity and the volume of the solution of the HCl to get the moles of HCl, okay? But what it's asking for is the grams of CO2. This is actually a general chemistry 103 problem because it doesn't involve gases at all. It's just asking you for the grams of CO2. You could see that now later in the problem, you're asked to give what is the pressure of the CO2 in the container that it's collected in. But initially, part A is just a straight stoichiometry problem. So you're going to go from the molarity and the volume. So how do you do that? Well, you got to convert the volume to liters. Okay, and then you're going to use the fact that molarity is moles per liter. So it's 2 moles per liter. Okay, you multiply that out. So I was supposed to do that under here. Oh, well, it doesn't matter. And so this comes out to 1.05 moles of HCl. So I'm going to continue over here. So how are we going to get the amount of CO2? Well, we have to look at the reaction to see what the mole ratio is. And you could see that there's a 2-to-1 ratio of HCl to CO2. So we have 1.05 moles of HCl, then we have to use a stoichiometric ratio. We want to end up with the moles of CO2. And so moles of HCl cancels, and we're just dividing by 2. So we have 0.525 moles, but we need the grams. So now we have to multiply by the molar mass of CO2, which is 44.01 grams per mole. All right, so that's the end of that problem. That's the end of part A. So that's really like Chem 103, a stoichiometry problem. But so the second part of the problem is a little different, right? Because now here you're being given some additional information about the volume of the container, and you're given the temperature, and you're asked to find the pressure of the CO2 in the container, okay? So how am I going to do this? So, the ideal gas law is like that. So what do I know here, right? I know the temperature, I know the volume, and I also know the moles of CO2 because that was calculated over here. So what I'm going to do is solve for P. Okay. So it's just 0.525, 0.08206 times, well, 26 degrees C is 299.15 or 299.2. I'm keeping one decimal place because one was given. And the volume's 21 liters. And this comes out to 0.614 atmospheres. So this is what I would call a very straightforward gas stoichiometry problem. Did anyone want me to go over anything about that? Did you understand the whole problem? Is there a part that was confusing? Hold on, let me check something.
How did you know how many moles there were?
Hold on. Somebody wanted me to scroll up a little, so I'm going to do that. Oh, hold on. Is that okay? More? Now, what did you ask? How did I know how many moles there were? Well, remember how I did this. I started with the molarity and the volume of the HCl. Was it HCl? Yeah. And I calculated the moles of HCl. Then I used the mole ratio to get the moles of CO2. That's how I got the moles of CO2. Does that make sense?
Yes, thank you.
Okay.
I was overthinking it.
Yeah. Okay.
I just
all right.
have a question.
Yeah.
Did for the temperature, did it say it in the problem or did you have to find it?
Said it in the problem.
Oh, okay. I
Yeah,
think I missed that.
26.
Sorry.
There it is right there.
Oh, okay. Thank you.
Okay, so now I'm going to talk about what makes this a little more complicated in certain situations. So there's a complication that really happens a lot. And this complication is actually present in the second problem of the graded assignment 1, okay, which is problem number 22, which I'm not going to do, but you have to do for that. But I'm going to do very closely related problem, the problem I'm going to do right now. Well, anyway, so I'm just going to talk about a different reaction. And this complication is what happens when you are collecting the gas over water. So I'm going to draw a little diagram of what's going on here. Okay, so suppose we have a reaction of HCl and zinc solid to produce hydrogen gas and zinc chloride. And this is a pretty simple stoichiometry as well. A lot of 1s and 1, 2. But suppose that in this case, we collect the H2 gas over water. Now, what does that mean, collecting over water? Well, it means that you would start with, say you have your test tube where your reaction is happening. You got your zinc here and you got your HCl solution. And here's your zinc. And then maybe you have a piece of tubing that's going through a rubber stopper. So there's like a hole in the rubber stopper. and this tubing, okay? So you get the tubing. I'm going to continue with the tubing in a minute. So and then you have this pan, this tub of water. And what you do is you first put a graduated cylinder in here, and you fill it with water, and then you invert it. So here's your inverted graduated cylinder. And here's the level of the water. And of course, we know the water goes all the way up. Anybody remember why does the water go all the way up? It's because of the atmospheric pressure, right? It's pushing down here, it's pushing the water up there. All right, I'm going to erase that because that's a few days ago's class. So let's say we have this tubing, and this tubing, we put it into the inverted cylinder. So this is what it looks like initially before any H2 gas is produced. But if we wait a little while and the reaction starts to get going, right? And now we have these bubbles that are coming out, and we still have the same thing here. We have this tubing, and now our inverted cylinder starts to fill up, and it fills up with H2 gas on top, so that now maybe you have this picture. And here it looks like there's nothing there, but we've been seeing the bubbling action happening here. I guess I should draw the tubing. Okay, so you're seeing bubbles going up, and here's the H2 gas. Okay. But this gas is being collected over water, right? Because this is water here. So whenever you have a gas, whenever you have water in a container, you are always going to have some water vapor above that container, all right? Oh, my pen's not writing now. All right, hold on a second. In those situations. It's the old computer heating up. I'll be back. There's a lot of, hold on a sec. All right. Okay.
Diane. Join the meeting.
All right. Okay. See if it works now. Yes, it does. All right. So what you actually, so whenever you have a glass of water or a bottle of water, so here's a bottle of water, right? And let's say it's closed. And let's say the temperature is 25 degrees C. Here's your water. So you have liquid water down here, and you're always going to have some vapor. This is water vapor, which is, H2O gas. And we call this, the pressure here is the partial. So there's a certain partial pressure of water above the liquid. And I think you can predict what happens here. Let's suppose you heat this up and you keep it closed. Right, so here's your bottle now. It got fatter, right? And now let's say this water is at, 80 degrees. Okay, so you're going to have more molecules here in the gas phase at 80 degrees. This is like when you're boiling a pot of water, and you could tell that the vapor above that boiling, above that heating pot of water, you keep getting more and more water in the vapor phase above it. And that's what I'm showing you here. It turns out that if you keep this closed, that an equilibrium sets up, that you actually have water in the liquid going back and forth to the gas phase, some molecules going up, some going down. But if you keep the bottle closed, eventually you have equal rates of liquid going to gas and gas going to liquid. And at this temperature, so at 25 degrees C, there is a certain vapor pressure that stays. There's a certain pressure, and it's constant at any given temperature. It's constant for 25 degrees C. Now, when you heat it, now you throw off that equilibrium and you start throwing more molecules of the liquid into the gas phase, which we learn about a lot in part 2, unit 2. And what's happening is you're giving more energy to those molecules. So they're breaking away from each other and they're escaping to the vapor phase. And the more you increase the temperature, the more energy you're giving them to overcome attractions and to go into the vapor. But that's for the next unit. But anyway, if you heat it up and then you stop at 80 degrees, now you establish another equilibrium. But this equilibrium will have a greater partial pressure of water. And it is also constant as long as the temperature stays at 80 degrees, but it's higher. Well, I said it was greater, so that's good. Okay, so if we want to figure out the pressure in here, so we want the total pressure, we've got to worry about two gases, right? We've got the partial pressure of H2, and then we've got the partial pressure due to water. But this is pretty easy because this we can look up in a chart. Okay, so we'll easily be able to find that. What's going to be a little bit harder is finding the pressure of the H2. That's what we're going to get from the stoichiometry. So let me go on and work this problem out, and then I'll actually ask you to break into some groups and start working on some of these problems on your own, and I can come and help you. So first of all, I haven't given you anything in terms of like the amounts of anything reacting. So let's just say we have 2.41 grams of zinc reacts with excess HCl. Okay, so it's amount of zinc that's going to determine the amount. Let me write the reaction again. Zn plus HCl goes to H2 gas and zinc chloride. And this is balanced with ones. Okay. And so what are we trying to find out here? Well, and what are we given? So let's say that the temperature is 25 degrees C and the volume of the gas at the end of the reaction is 1.80 liters. So let me make sure you know what I'm talking about here. This is the 1.80 liters, right? It's just this volume of gases here, not the volume of the water. We don't care about that. Okay, so that's the volume at the end. And so what the question really is what is the pressure? What is the total pressure at the end of the reaction? Okay. And we talking about, of course, the pressure here, this P total. This is the thing that we want. And so what you have to remember now is that you've got P total is the sum of the pressure due to the hydrogen gas and the pressure, which is the vapor pressure due to water. This is a constant. This you can look up in a table, which I'll give you in a few minutes. And this we have to calculate. And how are we going to calculate it? Well, we have the amount of the zinc. we can convert the grams of zinc to the moles of zinc. So then what I want to do is I want to find the moles of the gas. And this is the only gas that's produced in this reaction. So you don't want to bother calculating the moles of that. You want to calculate the moles of the H2, and you're going to use the stoichiometry to do this, the stoichiometric ratio, right, which is very conveniently 1 to 1. So the moles of zinc is going to be equal to the moles of H2. Okay, once we get the moles of H2, then we're going to find the partial pressure of H2. And how are we going to do that? Well, we're going to use the ideal gas law for the hydrogen component. Okay, and we know the temperature, we know the volume, and we will have calculated the moles of H2, so we'll have that as well. Finally, that's not quite the end of the problem, because we have to add the vapor pressure of water at 25 degrees C. And when we get this sum, that is going to be our total pressure. Does anyone need me to explain anything about this method before I just go ahead and do it?
Yeah, can you explain that last part one more time?
Oh, so which last part? Adding the pressures together to get the total pressure?
Yeah. Right before that, I mean.
So you understand how you could use the amount of zinc you started with to get that's the grams of zinc to get the moles of zinc. And then you could get the moles of H2 from that. But now we're going to remember that when we have a gas mixture like we have here, you have the partial pressure due to each component, and that depends on the moles of that component, which is what we have just calculated here once we get to this point in the problem. So you'll take moles times RT over V. That's really, notice that's PV equals nRT, right? For pH2 and NH2. That's how you'll get the partial pressure of H2. And then to get this, you have to just look it up on a table, which I'll show you in a minute. Okay?
Okay, thanks.
Good. All right, so I'll get a little space here because this is I'm not quite ready for this table. Oh, come on. Actually, I'm going to move it this way. Oh, come on. It doesn't want to go. All right, that should be plenty of room. Okay. All right, so let's go back to the 2.41. Okay, yeah. 2.41 grams of zinc. 1 mole of zinc is 65.38 grams, 0.0369 moles of zinc. And don't just round that to 0.037, right? You're given 3 significant figures here. 1, 2, 3. You have more than 3 significant figures here, so you want to keep your 3 at the end. 1, 2, 3. All right. So 0.0369 moles of zinc. Now I'm going to use that. Kind of messy. And, looking back at the equation, remember we have a 1 mole of zinc gives 1 mole of H2. So we have a 1-to-1, but don't expect this in every single problem. Don't assume that you're going to, whatever the moles of the reactant is, don't assume that's the moles of the product, right? You need to worry about the stoichiometric ratio, which here is 1-to-1. So it's 0.0369 moles of hydrogen. So now pressure of hydrogen is N hydrogen RT over V. So 0.0369 moles, 0.08206. What was T? 25 degrees C. So that's just 298 Kelvin over, and the volume is 1.80. Please keep the sig figs. Zeros at the end are significant, so you must keep them. And so you end up with, let's see. Point 501 atmospheres is pH 2. Let me show you something else. Notice that this is less than an atmosphere. And from the picture, it has to be less than an atmosphere, because what we had in the pan there at the end was we had a situation kind of like that. So notice that this level of the water on the inside is not the same as the level on the outside. So this is the pressure that the atmosphere is pushing with. What's pushing in here is the pressure of the gases. And most of that is due to hydrogen. And so you could see if this was going to be 1 atmosphere, then these levels would be the same. But the gases are pushing less than the atmosphere. That's why the level is higher. If it were pushing the same, then the water level would be down in the middle. So actually in lab, you're going to use the fact that when the level is the same inside and outside, the pressures are the same. Well, in this example, the pressures are not the same. And in fact, I know from looking at this, because the gas inside is not pushing down as hard as the atmosphere, that it would have to be less than an atmosphere, because atmospheric pressure is basically 1 atmosphere. So I don't know, maybe I shouldn't have said that, but that's just another little thing. All right, so that's the partial pressure of H2. What about H2O? Right, so I said you have to look this up on a table, and you do. And here's the table. Okay, temperature, vapor pressure of water. Usually this is given in torr. So that's, if you circle, this is 25 degrees C. At 25 degrees C, you have a partial pressure of H2O is 23.8 torr. Well, you know, if I'm going to add pH2 and pH2O, they have to be in the same units. So, you know, I could either switch this to atmospheres or switch this to torr. I usually put everything in torr, but it doesn't matter at all. So 0.501 atmospheres. So what will I put in here? Do I divide by 760 or multiply?
Multiply.
Good. So that comes out to 381. Okay, and so I'd add, that's pH2. So 381 plus 23.8. Okay, so I have 3 sig figs here because I had 3 here, and I have, well, this is considered exact. When I add these, I'm going to have to round to the units place, because when you add, the number of sig figs depends on the number of decimal places in the one with the fewest. And the 381 has no decimal places. So this comes out to 404.8, but I would report my answer as 405 torr. Okay, because I have to round to the units place, so I have 3 significant figures at the end. Well, I have to round it because I had no decimal places here. That's why I have to do that. And I do end up with 3 sig figs. I could transfer this to atmospheres if I wanted to, but it depends on what's asked in the problem. Okay. So that's how you handle the vapor pressure of water. And that's beginnings of doing gas stoichiometry problems. And let's see. So there's problem number 20, problem number 22, and problem number 23, which are, on different activity sheets, but they're all numbered in sequence. Problem 20 is activities on activity 6. 22 is in the graded assignment, but it's also from activity 8. And then number 23 is activity 9. And anyway, these are good problems to work on. Why don't you could start by working on the one that has to be handed in. So that's what I'm going to open the breakout rooms for. I go to all the breakout rooms, so don't feel like I haven't gotten to your room yet. You can summon me as well. But yeah, we'll get to all of them. And there were, if you have a question at the end, or you want to get out of the breakout room, you can go out to the main room. I could help you there even. So, there you can message me. I'll look at the chats. And if you have a problem about something. Somebody's asking, when will this recording be put up on Blackboard? I have to wait to get the email, and then I have to, download it and put it up. I usually put it on YouTube, and I put the link from Zoom, and yeah, it depends, because sometimes I get the Zoom recording like an hour after class. Sometimes I get it 2 hours after class. Sometimes it's a half an hour after class. It's hard to predict. I don't know. All right, so there's another thing I want to tell you. Okay, so we have the graded assignment 1, which is due Sunday. I just want to, because my lab is on Tuesday, so the lab next week, the handouts will be up over the weekend, and it's going to be copper week 2. This is for next week, obviously. Section 2 has to still do the lab this week. And I'm also going to post a video on the kinetic theory. Which I'm going to be covering. This is what we're going to be doing on Tuesday. Oh, sorry, on Monday. We used to have Tuesday, Thursday. And I think that it'd be great if you could watch it before February 1, before Monday. There will be quite a bit of overlap between it and what we do on Monday, but it's in more detail on the video. So that'll be on YouTube. And I'll post, all of my Chem 104 Spring 2021 videos are, you can find them all in by the same link, but look for the one that says something like kinetic molecular theory. Okay, so I'm going to open up those rooms unless anybody wants to say anything else before I do. Questions or anything? Okay. Hi, room one. Is this room one? Hmm. Hmm. Hi, you got, anybody want to ask me a question in the main room? Edward, Isabella? Are you actually there?